Hello, my name is James Parr, and I'm very happy to be presenting this talk on Beyond Reproducibility at FDL. I'm going to be joined in a moment by my colleague Mark Cheung, who's really going to provide the meat of the substance in this talk. And he's going to take us through the SDOML dataset. But I thought I'd kick off just with a few slides on how we've been thinking about reproducibility, but also open science. So over the last few years, we've been working to make our science more open, and it's exciting to see organizations like UNESCO start carrying the torch on this. And UNESCO's Open Science Charter talks about transparency, verifiability, reusability, and inclusiveness, which are, of course, all important ideas. And it's sort of interesting because, of course, as soon as you start thinking about this, you realize that being open is more than just reproducible. And this is really, some of the conundrums and questions that we've been trying to tackle. So good scientific AI is not just about the provision of analysis-ready data, code and papers, although that's an excellent start. Open science is living science, and that's perhaps obvious to say. It's always changing, it's always morphing, but certainly in the field of AI, it's perhaps worthwhile understanding this a little bit better. We often have this conundrum about how we take our AI research that sort of comes out of the oven at about TRL, Tech Readiness Level 4, and then we have to figure out how to get it to a research impact product at TRL 8. And it's easy to think of this as being a linear or monotonic type process, but of course, we know that it's much more unpredictable than that. The data changes, the instruments change, the labels change, the context drifts, the models change, even the verification changes. And so when you're deploying or maturing AI, it's always a lot more complicated than it seems. So I really like this cartoon, this caveman explaining that, that perhaps the wheel might be a good idea. And this is often the problem when projects are scoped. They're not scoped for unpredictability. They're not scoped with the sort of need for constant experimentation. And the result, of course, is compounding technical debt. And because of that, you end up with white elephants, which, of course, plenty of AI projects tend to be. So we've been trying to think about how we plan for this, and perhaps a sort of way of thinking about this, again, thanks to our colleague Alex Levin from the Institute of Simulation Intelligence, is sort of this acknowledgement that the journey to high tech readiness is non-monotonic. And so when we say open AI is living science, it's also non-monotonic science, and that means that we need to plan for that change. So how do we do that? How do we create living non-monotonic science? The sort of solution we've come up with is to really try and understand this balance between iteratively enhanced data, model improvement, and then reproducible, well-annotated code, and sort of make it, put it in a place, a platform where it's easy for people to get onboarded and understand what they're looking at and feel confident about the work. So we asked a few more questions, like once we have done that, and what other, if you like, what's the second order of questions that get unlocked? How do we make the science more open? What do we mean by AI readiness? Do we need common standards? And quickly realize that there's a complexity ceiling, like this is impossible to manage this all with traditional project management tools. So of course the answer is this notion of community-driven continuous optimization. How do we get the community maintaining these things and doing it in a way where the standards are exemplary and it happens sort of on behalf of everybody? And really that's the dream. So this is what we've been experimenting with, and I wanted to show you a little bit about what it looks like. And so perhaps worthwhile remembering Alex's diagram to high TRL. And we've tried to turn that diagram into something that sort of makes sense. This idea of a series of processes that take us through MLOps deployment, but also the integration of communities. So there's a wrapper of expertise that's being built around all of the research. What does it mean? Easily accessible project onboarding, really making it easy to understand what's going on, do an experiment without having to download a lot of data, having it ready for you to try out on the cloud. Component tools, so realizing that deployed systems are essentially made of component modules, but let's package those modules and make them usable and transferable to other use cases. And then version data, of which Mark will tell you about in a moment. So really that's the overview, that's the appetizer. I hope that sets up the conversation for Mark in a few moments. I just wanted to say thank you to our SpaceML community, everybody involved in helping us get to this point. And with that, I'll hand over to Mark.
Thank you, James. This is Mark Cheung from Lockheed Martin's Solar and Astrophysics Lab. I work with NASA's Solar Dynamics Observatory mission, which has been continuously monitoring the sun since May of 2010. And there are 3 instruments on board SDO, which have captured about 500 million images since launch. And a set of these images are featured in the US Postal Service's 2021 stamps, released a few months ago. And if you haven't seen them in the flesh, I would highly recommend you order one for yourself, because they're absolutely stunning and make for a great holiday gift. This is an example of what images taken by the Solar Dynamics Observatory looks like as the sun evolves in time. It's a highly compressed movie showing 10 years worth of SDO data in 1 minute. Now, by and large, SDO observes the sun all the time, and you can see the sun is spinning about once a month, and the data quality looks pretty uniform, but sometimes there are artifacts. And there are some more subtle features. For example, because of the eccentric orbit of the Earth around the sun, the apparent size of the sun on the image changes throughout the year by a few percent. So there are these artifacts and nuances in the data which make it not immediately ready for the data to be used in machine learning purposes. Sometimes we have anomalies on the instruments and the cameras are offline for a while. Sometimes the spacecraft off points for some calibration maneuvers. So in order to create a machine learning data set, it really helps to go to the source and have the instrument teams involved. And that's what we did with SDOML. The motivation for a machine learning dataset from the mission itself is because we started to notice that more and more teams are starting to use SDO data and apply machine learning techniques to solve certain problems. However, whereas the science-grade and browse data products are available to anyone because of SDO's open data policy, unless if you're a heliophysics domain expert, it really is difficult to know where to begin and what are the idiosyncrasies of the data. So we noticed that various groups were doing this, and some of them were scraping, for example, JPEG files to create their own computer vision datasets, but they were unaware that the scaling used to create the JPEGs had color maps that essentially varied with time, with the age of the mission, in order to compensate for degradation, but it wasn't done in a way that was scientifically accurate. So our goal was to release a standardized ML-ready dataset that has been appropriately prepped and useful for diverse problems. So we take into account of throwing out data with artifacts during calibration maneuvers. We take into account that the size of the sun changes, so we standardize that. We compensate for the degradation in the sensitivity. and align the images from the different instruments as well as the spectral irradiance, aligning it in time with the rest of the images. And the data was published in an AppJ article and released via Stanford Digital Repository. And these SDO images in the first version of SDO ML were grouped by wavelength and time and saved as NumPy files, which were then consolidated into tarbors. And for about 8 years of data, it totaled about 7 terabytes. So SDO ML version 1 has been used for a number of problems, a number of scientific and machine learning papers, tackling problems such as image translation, for example, to translate from one extreme UV wavelength to another. For gap filling, for example, one of the instruments stopped taking spectral irradiance data, and we trained a machine learning model to take images from the EUV telescopes to monitor the spectral irradiance of the sun in the extreme ultraviolet. This is a paper published in Science Advances. So in many respects, SDO ML version 1 was a success. But there were shortcomings. For example, for someone to start using the SDO ML version 1 data, you had to wait a long time. You had lengthy download times from the Stanford Digital Repository. It wasn't particularly fast. The way the files were saved, it was inconvenient to spatially subsample the data, those NumPy files. There was a lack of metadata in the files that scientists like. And then there was a lack of tutorial notebooks to kickstart experimentation. So from the community request, we decided that we would revise SDOML and create a new version. And a preview of the second version of SDOML is now available on the SpaceML repo. Here, if you go to this link and click on the SDOML example, what you will find are links to a GitHub repository, as well as a link to a Google Colab notebook, which allows you to immediately spin up an instance and then interrogate the structure of the data and inspect some of the images in the SDOML dataset. The format we chose is a ZAR format, which is designed for chunked n-dimensional data, and it works very well with Dask. So that allows us to apply parallel processes and lazy evaluation to workflows. So that's very useful. And all the tooling that is based on Dask then can be applied to performing workflows on SDOML. So that's great. And then the Colab notebook also shows you how you would generate a scientific data object that scientists actually like to use. The package of choice for heliophysicists with solar and especially solar astronomical data is a SunPy, which is based off AstroPy. And so with this notebook, a machine learning practitioner interested in solar dynamics observatory data now has a way to know what is the workflow that scientists have. We think of the first version of SDOML as a minimum viable product, if you will, and it allows us to show and demonstrate the potential of applying AI and machine learning techniques to the solar dynamics observatory data for science and engineering. But it also allowed us to get feedback very quickly from the community on how we can do better, how we can improve on the data processing, on making the data more available, of decreasing the friction and the barriers in order to start doing this work. And SpaceML is the platform that brings this all together to accelerate open science. And there are many more examples on the spaceml.org website, and we encourage you to explore and join the community. Thank you.